Hello, this is Dr. Brown. In this really quick video, I'm going to give a quick illustration of average rate of change versus instantaneous rate of change. This video is going to be very quick. It's going to hopefully give a little more insight into what we call instantaneous rate of change in calculus versus average rate of change. Now, everybody already knows everything about a linear equation like f of x equal 2x minus 4. The slope is equal to 2. And anywhere along this line, the instantaneous rate of change is exactly the slope of the line. As you go up this line, say you were climbing this, the slope is always the same. So the average rate of change from, say, this point to this point, or from this point to this point, would be just the slope of the change in y divided by the change in x. Now, however, if you go to a function that is nonlinear, in fact, this is one that's quadratic, and you wanted to find the slope at any point, it's not quite obvious how you do that. Suppose what we're going to end up with in this video is trying to find out what the instantaneous rate of change is at the point 4 and 1. If you plug 4 into f of x, you get that the value is 1. Now, the first thing we're going to do, though, is talk about the average rate of change, the ARC, I call it. And now we're going to look at the point 4 and 1, and we're going to look at the point 7 and 25/4. In other words, we're going to look at these 2 points and calculate the average rate of change. And I'm going to try to do it just right here on the side. We want the average rate of change from 4 to 1 to 7 and 25/4. And the average rate of change is going to be y2 minus y1 divided by x2 minus x1, which is the same as f of x2, the second x value, minus the first x value, divided by the difference in the x values. And plugging in, you will see that is 25/4 minus 1. That's a change in the y value, divided by 7 minus 4. And that is equal to 21/4 divided by 3, which is 7/4, which is equal to 1.75. So as you go from this point to this point, the average rate of change is 1.75. Now, getting back to the quadratic again, if we want to find the instantaneous rate of change at 4 and 1, we have talked about drawing a tangent line. We're also going to do this by calculating a limit, as we've already talked about in a moment. But let's just say we wanted to estimate this, the instantaneous rate of change. And this is similar to one of the problems you had in the homework if you started doing the homework. And what I did was draw at the point 4 and 1 a very squiggly line, which I think is sort of close approximation of what we call the tangent line. That's what we're doing here when we start doing calculus, is to look at a point and draw a line that touches at just that point, and we call that the tangent line. Now, if we go a little further, we want to calculate the slope of that tangent line. So I've already sort of drawn something here that shows you a little triangle that looks at the rise divided by the run, which would be the slope of that squiggly line, roughly. It's an approximation. So, but the instantaneous rate of change here would be the slope of that line, and I'm going to use approximation symbols as being 3.25 divided by 3, which is equal to 1.083. So estimating the instantaneous rate of change at that point is 1.083. Now I'm going to go to an example of an app we're going to use in a moment to show you how we calculate the instantaneous rate of change exactly. Let's go back to the point 4 and 1, and let's go to another point where x is equal to 4 plus h. In other words, we're adding h to the x value of 4, and then looking at what the value of the function will be at x equal 4 plus h. And well, obviously it's going to be f of 4 plus h. And what we will do is calculate the change in the y divided by the change in the x value. And we're going to move this point along. And I was able to find a pretty neat app that allows you to do that. If I can find it here. Okay, here it is. In fact, you can go find it yourself at the link up here. But here is our equation, 1/4 x squared minus x plus 1. Here's a point we're trying to find the slope of the tangent line, or the instantaneous rate of change. Here is the point that is h, the x value is h points away from 4. Now notice we have an app over here. It's calculating the slope over here. I'm pointing at this, the slope of that secant line, which is the slope from here to here. And notice it tells you what it is. In this particular point, it's 1.74. If we actually move this exactly to 7, if I can get it exactly on 7, I can't quite get it exactly on 7. Oh, I know what I can do. I can make h equal, well, that's good enough. H equal 3. Anyway, if we get closer and closer, making h now is 2.0, h is 1.4. The 2 points are getting closer and closer together. H is getting closer and closer to 0. And if you'll look right here, the slope of that secant line is 1.175. Remember, we estimated the slope would be 1.08. And notice as you get closer and closer to the point, the tangent line and the secant line become the same. And as you get there exactly, it's getting closer and closer to 1. And I would bet you that the actual value is going to be 1. So what we have here is this line is the actual tangent line. This is the secant line. And as they get closer and closer, they are going to be right on top of one another. Now I'm going to actually calculate this. We just did the animation. Now we're going to calculate the instantaneous rate of change. And remember, we said that the IRC, I'm going to call this IRC, it's going to be the limit as h approaches 0 of the value of the function at 4 plus h minus the value of the function at 4 divided by h. Now, if you just plug in h equals 0, you get 0 over 0, which doesn't mean anything. However, we will be able to calculate this limit by plugging in and simplifying it. We need to calculate f of 4 plus h. Well, the f of x, remember, is 1/4 x squared minus x plus 1. So plugging in 4 plus h everywhere you see an x, we get 1/4 4 plus h squared minus x, which is 4 plus h, plus 1, minus f at 4. Now remember, if you plug in 4 into f of x, you know that that is 1. So that's minus 1 divided by h. And this is equal to the limit as h approaches 0 of 1/4 x squared, which is 16 plus 8h plus h squared minus 4 minus h. 1 and minus 1 is 0. And then we divide this by h. And we get the limit as h approaches 0. This is 1/4 of 16 is 4. 1/4 of 8h is 2h. Plus 1/4 h squared. Minus 4 minus h all over h. Now notice when you do this, a lot of interesting things begin to happen that make some of your problems go away. The 4's cancel, and I finally get 2h minus h, which is h, plus 1/4 h squared divided by h. We want the limit as h approaches 0. And we can factor out an h here. We get h on the 1 plus a quarter h divided by h. The h is canceled, and the h being 0 is no longer a problem. As h goes to 0, the limit is 1. And that is exactly what the app told us it was going to be as we got closer and closer to the 0.4. And remember, our estimate was 1.08, which was a fairly good estimate. But anyway, the instantaneous rate of change at that point was 1. And that's a real quick demo of how you do this.